I come to the session 13. Continue the same in session 12. So we continue in the same. So we come to the consider the power series. I can write summation a n z power n equal to summation un of z. Say summation un is convergence if the root test summation n tends it a root test limit n tends to infinity absolute values of un power 1 by n less than 1. See, this implies a limit n tends to infinity the power series an zn whole power 1 by n less than 1. This implies limit n tends to infinity an whole power 1 by n into mod z less than 1, because n and get cancelled. Suddenly say limit n tends to infinity an whole power 1 by n into absolute values of z less than 1. Less than 1. Yeah, taking limit n tends to infinity. Taking a limit n tends to infinity, absolute values of an whole power 1 by n is equal to 1 by r, capital R. So we get mod z less than r less than 1 or mod z less than r. So this is a less than 1. If we take this constant, limit n tends to infinity, if we take this constant, mod absolute values of n whole power 1 by n, I have to take denote the number r. So we can suddenly we can write limit n tends to infinity absolute values of n whole power 1 by n is equal to 1 by r. We get so absolute values of z divided by r less than 1 r, simply say absolute values of z less than r. Thus the power series an z power n is convergence or divergence according as mod z less than r or mod z greater than r. So the series is convergence either the series is convergence depending on r. If r less than 1 is a convergence, if r greater than 1 is divergent. Means that is where you say if a convergence mod z less than r, if mod z greater than r. So if the power series a n z power n is convergent mod z less than r, the divergence mod z greater than r. Corresponding to the every power series summation a n z power n, there exists a non-negative real number, say r. There exists non-negative real number, say r, such that mod z less than r. If the series is convergence and if mod z greater than r, if the series is divergent. So yeah, this is the series depend on r. If mod z less than r, the series is convergence. Mod z greater than r, if the series is divergence. Now, if we draw a circle of radius r, so if we take a circle of a radius r, if radius r with the center as origin, the center as a origin, then the first one, the power series summation a n z power n is convergence for every z within their circle, mod z less than r. Second one, the power series summation a n z power n is divergence for every values of z outside the circle. So it's a divergence for every values of z outside the circle, mod z greater than r. Such a circle is called circle of convergence. Such a circle is called circle of convergence, and it is radius r is called radius of convergence of the power series summation a n zn. So there are three possibilities for r. So now this is convergence divergent depend on r. There are three possibilities. Suppose if r equal to 0, if r equal to 0, in this case the series is convergent only when z equal to 0. If r equal to 0, the series is convergence only when z equal to 0. Second one, if r is finite, in this case the series is convergent at every point within this circle and is divergent at every point outside this circle. So means if r is finite, in this case the series is convergence every point within this circle is convergent. Within this circle is everything is convergence, and is a divergence at every point outside the circle. Now, third one, if R is infinity, if R is infinity, in this case, the series is convergence for Z, for all Z. The series is convergence for all Z. Remark, for all Z. Suppose if take a remark, 1 by R is equal to limit n tends to infinity, an, root test I'm saying, limit n tends to infinity mod an whole power n is equal to limit n tends to infinity an plus 1 divided by an. Limit if you apply the ratio test, root test and equal to ratio test, limit n tends to infinity, absolute values of an plus 1 divided by n. This follows from the Cauchy theorem on limits. So, we take some problems, also we take a few problems we discussed. One is convergence, one is divergence. Suppose we find the radius of convergence of the following power series. Summation Zn power n power n. I take one example. For example, so if we have summation Zn whole power n, Zn whole power n divided by n power n. The comparison test we say summation an z power n. We get, suppose an here 1 by n to the power of n. Now 1 by r is equal to limit n tends to infinity, absolute values of n whole power 1 by n is equal to limit n tends to infinity 1 by n power n whole to the power of 1 by n. So if we take this equal to n and get, so n to the power of n and get cancel, simply we get limit n tends to infinity 1 by n. So if a limit n tends to infinity 1 by infinity, suddenly 1 by infinity is 0. Suddenly 1 by r equal to 0, so that r is equal to infinity. So if you take one more example, summation 2 power minus n zn divided by 1 plus I n square. 1 plus I n square. So here, if you take an here, 2 power minus n divided by 1 plus I n square. an is equal to 2 power minus n divided by 1 plus I n square. Yeah, again 1 by r is equal to limit n tends to infinity. Take a root test. An whole power 1 by n is equal to limit n tends to infinity 2 power minus n divided by square root of 1 plus n raised to 4 whole to the power of 1 by n. So ratio test and if you like. So this is equal to limit n tends to infinity. If you simplify, we get, so if n, so we get simplify, we get, so 1 by 2 of 1 plus n raised to 4 whole to the power of 1 by 2n. So again, if you apply the limit n tends to infinity, 1 by 2 is constant, you take into 1 by n whole raised to 4 whole to the power of minus 1 by 2n. Again, this is the limit n tends to infinity, 1 by 2 into n square whole power 1 by n of 1 plus 1 by n raised to 4. So we take n raised to 4 as a common on the outside, whole power minus 1 by 2n. Now again, this is equal to 1 by 2 times of limit n tends to infinity 1 by n raised to 1 by n whole square of 1 into minus 1 by 2 n raised to 5 etc. by using the binomial expansions x plus a whole power n like us. So we get, so only with the first two term is enough. 1 by 2 into limit n tends to infinity 1 divided by n to the power of 1 by n whole square of 1 minus 1 by 2 n raised to 5 plus etc. This is equal to limit n tends to infinity. This is get, this term will be get is 1. So 1 by 2 into 1 into 1. So we get 1 by 2. For limit n tends to infinity, n to the power of 1 by n is 1. We know the nth root there. So therefore we get is equal to r. 2 r, capital R is equal to 2. This is a finite term. It's a finite number. Again, we take one more example. If we take n fact, n is equal to n factorial square. n is equal to n factorial square divided by 2n factorial. Again, you apply the ratio test. An plus 1 is equal to n plus 1 factorial square divided by 2 of n plus 1 factorial is equal to, if you remove that factorial, n plus 1 into n factorial square divided by 2n plus 2 into 2n plus 1 into 2n factorial. So expanding to n factorial, 2n plus 2 factorial, I can write 2n plus 2, 2n plus 1 into 2n factorial. Again, I apply the ratio test formula. An plus 1 divided by n is equal to n plus 1 whole square divided by 2n plus 2 into 2n plus 1 is equal to n plus 1 divided by 2 into 2n plus 1. Here, some term get cancels. Here, n plus 1 whole square is that I take 2 as a common. Here, n plus 2 into n plus 1 we get. Again, 2n plus 1 as it is. So, n plus 1 term get cancels. We left n plus 1 divided by 2 times of 2n plus 1. Now, again, I take n as a common in the numerator. If you take n as a common in the numerator, n times of 1 plus 1 by n. Again, I'll take a 2 as a common, 2n as a common. We get 4 times of n into 1 plus 1 by 2n. So, n get cancels. 1 plus 1 by n divided by 4 times of 1 plus 1 by 2n. So, again, if we take 1 by r is equal to limit n tends to infinity, an plus 1 divided by an is equal to 1 plus 0 divided by 4 times of 1 plus 0. Suddenly we get 1 by r. So that r is equal to 4. So again, here r is finite. So again, r is finite. Now, if we take one more examples. So if an is equal to n factorial divided by n power n. So again, apply the ratio test. An plus 1 is equal to n plus 1 factorial divided by n plus 1 whole power n plus 1. Yeah, again, n plus 1 into n factorial divided by n plus 1 into n plus 1 whole power n. So n plus 1 term multiplied by n plus 1 and the numerator and denominator get cancels. We get n factorial divided by n plus 1 whole power n. Again, apply the ratio test formula. An plus 1 divided by an is equal to n power n divided by n plus 1 whole power n. The denominator, I take n power n as a common. We get 1 plus 1 by n whole power n. So n power n get cancelled. 1 by e is left by the definition of that. So 1 by e is. So 1 by r is equal to limit n tends to infinity. 1 divided by 1 plus 1 by n whole power n is equal to 1 by e is get. So r is equal to e. R is equal to e. Now, so this is the way we can, by using the theorem, and the theorem of the statement of the theorem. When is convergence, if r equal to 0 is convergence, if r is finite is convergence, r less than 1 is a convergence or divergence in the unit circle. If r less than 1, the whole point less than 1 means all lies in the unit circle is convergence. If all point lies in the unit circle, suddenly is a convergence. If all point lies outside the circle, is a divergence. By using the statement, we can solve some few examples, some problems we can prove this is a convergence and a divergence. Now you come to the some example. Further take some examples. So find the radius of convergence of the following power series. For example, we take summation n run from 0 to infinity 3 plus 4i whole power n into z power n. So summation n run from 0 to infinity 3 plus 4i whole power n into zn. So again here an is equal to 3 plus 4i whole power n. Again, then absolute values of an is equal to absolute values of 3 plus 4i whole power n is equal to square root of 3 square plus 4 square. 3 square plus 4 square whole power n. Now I am simplifying this here. So this equal to 3 square is 9, 4 square is 16. 9 plus 16 is 25. So square root of 25 is 5. 5 to the power of n we get. So again, 1 by r is equal to limit n tends to infinity. We apply the n through test. An whole power 1 by n is equal to limit n tends to infinity. Pi power n whole power 1 by n. Suddenly we get 5. So r is equal to 1 by 5. So it's a finite quantity. So again, we take a second example. We take this. We have summation minus 1 power n into z minus 2i whole power n divided by n. So the comparing with the summation an into z minus a whole power n, we find that a is equal to 2i, which is a center of the circle of is convergence. I simply say this is there. Simply say this is center of the circle. Now again we take an is equal to minus 1 power n divided by n. So an minus 1 an plus 1 is equal to minus 1 power n plus 1 divided by n plus 1. So an we get an plus 1 is equal to minus 1 power n plus 1 divided by n plus 1. By apply the ratio test, an plus 1 divided by an is equal to n divided by, if you simplify, so minus 1 power n is odd. So minus 1 power n plus 1 we get. So minus 1 power n get cancelled. Simply say minus 1 power 1 we left. So we get negative sign. So minus of n divided by n plus 1. So here, if we simplify an plus 1, you get minus 1 power n plus 1 divided by n plus 1 divided by minus 1 power n divided by n. If you 1 times minus 1 power n on term get cancelled, minus 1 power 1 we left. So again n divided by n plus 1 we get negative. Again 1 by r is equal to limit n tends to infinity. 1 by r is equal to limit n tends to infinity. An plus 1 divided by an is equal to limit n tends to infinity n divided by n plus 1. Again if we take n as a common, so limit n tends to infinity, n of 1 plus 1 by n. For again 1 get cancelled, simply say limit n tends to infinity 1 divided by 1 plus 1 by n. So if we limit apply this, 1 divided by 1 plus 0, suddenly 1 divided by 1, suddenly we get 1. So here r is equal to 1, again it's a point. So one more, if we take one more example, if an is equal to log n whole power n, an is equal to log n whole power n. So 1 by r is equal to limit n tends to infinity an whole power 1 by n is equal to limit n tends to infinity log n whole power 1 by n. Log n whole power n 1 by n. So n power n, so n get cancelled, simply limit n tends to infinity log n is infinity. So 1 by r is infinity, suddenly r equal to 0. So now we come to that. See one more problems here. So here an is equal to n into root 2 plus I divided by 1 plus 2in. 1 plus 2in. Yeah. So absolute values of n is equal to n root 2 plus I divided by 1 plus 2in. So again if we apply this, 2n square plus 1 divided by 4n square plus 1 whole power 1 by 2. So again the 2n square, as I take a common, we get 2n square divided by, again in the denominator 4n square we take common, whole power 2n square divided by 4n square whole power 1 by 2 half 1 plus 1 by 2n square divided by 1 plus 1 by 4n square whole to the power of 1 by 2. So again if you simplify, 1 by r is equal to limit n tends to infinity. 1 by r is equal to, here if we are taking 2n square as a common divided by 4n square as a common, whole power 1 by 2 you get 1 plus 1 by 2n square whole power 1 by 2, again divided by 1 plus 1 by 4n square whole square. So again 1 by r is equal to limit n tends to infinity, absolute values of n whole power 1 by n is equal to limit n tends to infinity. If you simplify here, 1 by 2 4 we get 1 by 2 we left, n square get cancelled, 1 by 2 whole power 1 by n. So if we take root 1 divided by 2 power 1 by 2n, of 1 plus 1 by 2 n square, 1 by 1 for n square whole to the power of 1 by 2. So, if we limit n tends to infinity, 1 by infinity is 0, 1 by 2 power 0. So, 1 by 2 power 0 is 1. So, 1 divided by 1 into 1. So, certainly we get 1. So, limit r is equal to 1. So, what about if we limit n tends to, if we apply the root test, p-test, the p-test form, limit n tends to infinity 1 by n raised to p zn. So again this compared to power series form summation a n z power n. Here a n is 1 by n raised to p. So that 1 by r, so that 1 by r is equal to limit n tends to infinity absolute values of a n plus 1 divided by a n is equal to n raised to p divided by n power n plus 1 all raised to p of 1 by 1 plus 1 by n whole power p. So here again I simplify n power p divided by n power p as I take a common 1 plus 1 by n raised to whole power p. So n by p get cancelled. Again 1 divided by 1 plus 1 by n whole raised to p. So 1 by e power p, 1 by e power p get cancelled. Simply say 1 divided by 1 whole over p. So 1 divided 1 to the power of p. Again 1 divided by 1 is 1. This is the r is a finite here. So again limit n tends to infinity 1 by n raised to p z power n. Limit the power series summation a n z power n. Then a n is equal to 1 by n raised to p. So that 1 by r is equal to limit n tends to infinity absolute values of a n plus 1 divided by n is n raised to p divided by n plus 1 all raised to p. So 1 divided by 1 plus 1 by n all raised to p. So if you take n raised to p in the denominator common, so n raised to p get cancelled. 1 divided by 1 plus 1 by n all raised to p. So 1 this is tag. So 1 divided by 1, because this term get cancelled. We get 1 divided by 1 plus 0 all raised to p. So 1 divided by 1 raised to p is again 1. So this is the r is equal to 1. This is the finite data. This is a finite quantity. Again this series is convergent. The series is convergent. These are the example for radius of the convergence. We give a theorem, we give some examples regarding the radius of the convergence.